Todd, perhaps we could get started.
Okay. Well, welcome everyone. Thanks for joining us today. My name is Todd Sweet, and I just have a few Zoom housekeeping items to take care of before I turn it over to our faculty hosts. So you'll notice, I think that with the exception of our hosts, we have participants muted and their video turned off just to minimize distractions and help ease the load on everyone's internet connection to make it a little bit more stable. We have also enabled the live transcript feature. So if you need closed captions, there is an icon at the bottom of your screen that will allow you to turn those on. And then finally, what normally in person, we would just let people ask questions as the presentation goes on. In this Zoom format, please use the chat feature, another icon at the bottom of your screen, and that will pop up a dialog box that will allow you to ask a question. And if you just want to type it in there, we'll be monitoring that chat throughout the presentation, and we can ask those questions to Professor Allen. So with that, I would like to turn it over to Professor Romit Roy Chowdhury, who is the faculty host for this series.
Terrific. Thank you, Todd. Welcome, everyone. Good morning. It looks like a first day of 70s today in Urbana-Champaign. That's exciting. Welcome to the Saturday Engineering for Everyone series, seminar series. To give you a quick background on this, Department of Physics at UIUC started this series where professors and researchers from the university were talking about their work and talking it in a way that's accessible to the broad Urbana-Champaign community. And we thought that's a great idea. And we thought that many of the exciting stuff happening at the engineering side of things, especially the electrical engineering and computer engineering side of things, we also thought it would be good to communicate those to the broader audience. So we started the series somewhere around 2014. And since then, it has been very exciting for us. From both the faculty and many of the audiences have come back to us and said that they've really enjoyed listening to it. So we would have this series in person in the Department of ECE on a regular spring, but with COVID, we couldn't do it in person. So we decided, hey, why not do it over Zoom as well? And it's very exciting to see already so many people who have joined in. And of course, this is being recorded, so this will be on the website, and you can tune in later and listen to it as well. So we've been continuing to do that, and there is a lineup of speakers this semester. I hope you have gotten the lineup of speakers already, and I think we will send out these announcements every time there is a talk coming up. I think 3 more speakers are lined up for the rest of this semester. One about COVID-19, which is, and how UIUC came up with exciting tests, saliva-based testing that's become the pride of UIUC across the whole nation, because we are able to test COVID from saliva without having to do your nasal tests. The next one after that is about remote sensing space, where we are talking about, Professor Waldrop will talk about how we can, what do we see when we look at Earth from 100,000 miles away. That will be very exciting. And the last one would be about robots and how robots are starting to interact like humans, and why we want to talk to robots who are who should behave like humans and so forth. So we have these exciting talks coming up. So please join these seminar series. We really are happy to talk to all of you about what's going on in our labs. Turning to today, it's a great pleasure to have Professor John Allen give us a seminar on the topic of desalination and how it actually influences climate change. To talk a little bit about Professor Allen is in the Department of Electrical and Computer Engineering at UIUC. He completed his PhD from the University of Pennsylvania, Philadelphia in 1970, after which he went to Bell Labs, where he enjoyed a 32-year at the AT&T Bell Labs Center. Professor Allen specialized in nonlinear cochlear modeling, auditory and cochlear speech processing and speech perception. He's a world-renowned expert in understanding how humans hear and interpret and understand sounds. And he has fascinating work and pioneering breakthrough research in this area. He joined Illinois from AT&T Labs in 2003, and since then he has taught and worked with his students on the theory and practice of human speech recognition. And he has more than 20 US patents on hearing aids, signal processing, and middle ear measurement diagnostics. He's a fantastic person and very, very excited and passionate about what he works on. Today, he's going to talk about applying his methods, which come from speech recognition signal processing, into a very different topic. And he's going to surprise us with his ideas on how water can be desalinated and how that could influence climate change in the long run. So I'll turn the floor to Professor Allen, and thank you, John, for agreeing to speak to us today. Over to you.
I hope I don't have to do anything. Todd?
We do not see your screen, or do we? No, we do not
Not
see
yet.
your...
Do you see the share screen at the bottom?
Yes.
You can go ahead and you have access to share your screen.
Okay. And I don't think I need that. So is everything good?
Things are great. Thank you very
Looks
much.
good.
Looks good.
Okay. So this is, with the exception of some things that were highly exaggerated in that wonderful introduction, I'm very, very pleased to be here. I gave this talk, it's kind of it was a dry run at Madison, Wisconsin on Wednesday. And after that, I felt a lot more comfortable about the whole thing. So hopefully there won't be any glitches. There weren't any glitches on Wednesday either. So when I learned about this problem of global warming, I had no question about whether it was true or not. It was true, and it scared the living daylights out of me. And I said, I want to do something about this. Now, that was kind of a strange thing because I didn't know very much about what I needed to know, but I was more than willing to learn. So this project has been around my life for several years, and it's reached a high point because it's now being tested in the mechanical engineering department, ME 147, I think it is, and it's in the second semester of doing that. So we're testing these ideas to build prototypes, and we hope that we can carry this on to something that's more than a prototype. So the objective is to deal with global warming. And in the process of thinking about that, I discovered another problem that's even more important than global warming, or you can't solve the problem of global warming without solving that problem, which turned out to be more immediate and probably arguably just as important, but maybe not, yeah. So that is how to desalinate water. So let's just talk about what the problem is. So the sun shines on us, and we look like a black body, and the sun looks like a black body. And if you don't know what that means, just think of a microwave. There's radiation coming in from the sun, and instead of heating the water, it heats the carbon dioxide, and the carbon dioxide then transfers the heat to Earth. Now, the surface of the sun is a mere 7,000 degrees. Inside is probably quite a few million degrees. And Earth, of course, is 25 degrees C. I'm going to work exclusively in the centigrade. I've been working a lot at trying to get myself to think centigrade. I'm not completely there. But in any case, at the surface of the Earth is about 1.3 kilowatts per square meter of energy that is power that's delivered to the surface of the Earth. That is a lot of power. So my idea was to harness the solar energy to desalinate water. So here's a pretty good description of the sun and the Earth. It's just completely out of scale. So this is 400 times further than the distance over on this side of the scale, and the sun is 400 times smaller or bigger than it's is being shown. But as the Earth goes around the sun, the axis, the Earth is on an axis that's at like 20 degrees or whatever it is. So it's oscillating back and forth. The sun shines on the south, then the sun shines on the north, and that's going to turn out to be an important feature of what's going on. So we used to have much less than the present amount of CO2, carbon dioxide. And when it got over 400 parts per million, it tipped the energy balance and it started becoming a problem, and the heat started to increase because the sun heats this carbon dioxide, and it has a lot of, there's a couple of places where the solar energy heats that carbon dioxide. Once it's heated, it can't lose that energy except to heating up the Earth. On Mars, which is an interesting comparison, there is 95% carbon dioxide, and it had an ocean of water 1 or several billion years ago, but that water has all disappeared. So the water on Mars today is gone. And hopefully this first video, which came live within the last year, you should be able to see this. So what this is showing is Mars. There's can you see this, everybody?
Yes.
Okay, I'm not quite sure how to make it full screen mode because
We can see it.
It's important. So this is Mars, and the solar cap, the Mars is being rotated, and the blue areas or the greenish areas, whatever that looks blue, were the billion years ago, those were the oceans. And as you can see, they disappeared. Now this is going to repeat itself one time. And it's so important because when there was water like this several billion years ago, there was not so much CO2. And we don't have a good metric of how much CO2 there was. But then the planet began to heat because the CO2 was building up and the ocean disappeared. There's some debate as to where it went. Some of it went into space, and probably some of it just froze and went into the interior of Mars. And so it all became a desert. And this is exactly what we don't want to happen to Earth, even in a billion years from now. But right now, we're at the threshold of worrying about this. Okay, I'll give you an opportunity to ask questions about these videos in a few minutes. We'll have a quick question Q&A session. Okay, so this is a demonstration that the significance of climate change. So this plot on the left there is showing the amount of CO2. And these units are a little strange, but let's not consider this. That's been removed from the screen. These units are correct over here. So this is a 20-year scale from 1960 to 2010. And this is a 5-year scale from 2015 to 2020. It doesn't quite get there, 2000, just before 2020. Okay, so there's two things to notice. First is this shows that the average amount of CO2 in parts per million is increasing. Not only is it increasing, but the slope has increased. So originally over here in 1960, the slope was about 1 2/3 parts per million each year, which doesn't seem like a lot, but over 20 years, 100 parts per million in 60 years. So it went from like 40 or 30 up to 400. It went from 300 to 400. And today it's more like 420. So this was in 1919, and at the peak and at the valley, there's some oscillation in the amount of carbon dioxide over time. It's locked to the time of year. So the slope has increased from 1 2/3 to 2 parts per million per year over the last in the last 10 or 20 years. Okay. Now, the next thing to observe is that the carbon dioxide oscillates. This tells us a lot because it decreases in the summertime and it increases in the wintertime. And it's absolutely locked. It shows it's sinusoidal averaged over most of the land mass. And this curve changes a little bit depending on where you measure, of course. If you measured it on the North Pole, you wouldn't see this cyclic effect, or on the South Pole, Antarctica. But if you measure it, I think this data was measured in Hawaii, and it was a University of Illinois professor who started making these measurements back in 1950. So this is a very clear effect that in the wintertime, in January, it goes up, and in the summertime, July, August, it goes down. And we know why that is. It's because of this previous slide I had where the Earth is tilted. So the sun is shining on the northern hemisphere or the southern hemisphere, and there's more foliage, there's more green stuff, there's more trees on the northern hemisphere, even given the Amazon. And so it goes down, and it goes down quite a bit, but it doesn't stay down that long. And then it comes back up, and it's in the bad phase of climbing during this half. And the net tendency is that it's going up. So we're at a very precarious point because it's going down during the summertime, but not as for long and not as much as we would like. We need to get rid of this trend. Okay, so what's the main source of climate change? It's the oscillations of the Earth where the sun is shining on the northern hemisphere or the southern hemisphere. So this is very convincing that the carbon dioxide plays a major role. It's not the only climate gas of causing climate change, but it is clearly the most important. Now, another thing that happens is that when the CO2 increases in the air, it's absorbed by the water. You probably know from Coca-Cola and from all these carbonated drinks that water loves CO2. And when the CO2 goes into the water, it creates carbonic acid. And carbonic acid lowers the pH, it lowers the pH, which means the acidity is increasing. And that kills the corals, which are a major point of life in the ocean. Okay, now the next thing, I want to just give you a little bit of thermodynamics here. If you started with ice at minus 273 degrees Celsius, which is absolute temperature, that would have been a long time ago. At some point, ice was rock solid. And as you start to you put in a constant amount of heat. So we're going to put in some heat Q, that would be in watts, or joules per second. We're putting in this heat from the sun. And what will happen is the ice would start to warm up, but it wouldn't thaw until it hits 0 degrees. At that point, the temperature is locked at 0 degrees. It's constant. And the ice is thawing. So it's no longer solid ice. Now you've got a mixture of ice and water. That will continue to happen until all of the ice is thawed. That might be 1,000 years from now. It might be 200 years from now. I mean, this is a known quantity. I think it's fairly far off, but it's not, not a million years. It's going to be in the next millennium for sure. I don't know the number, but it's not going to be forever because it's thawing pretty fast. I think it's probably difficult to actually estimate exactly when it's all going to be thawed. Once it's thawed, then you're out of this mode where the temperature is locked at 0 degrees and the water temperature starts to rise. This is big trouble because there's a lot of heat going in, and the water temperature, the oceans and the air are going to rise relatively quickly because there's quite a bit of heat. But water takes more heat to cause the temperature increase. So this slope and this slope are different. This slope is steeper than that slope for the same input. Okay, when all of the water gets to 100 degrees, we're no longer around because the oceans are boiling and turning into vapor water vapor. And eventually the water vapor goes into space and is carried away by the solar wind. And at that point, we start to look like Mars. That's shocking to me. Now, I've frequently heard people say we don't have enough water. Well, that's hardly true. We have the oceans. So we have plenty of water. The problem is you can't drink it and you can't use it to water plants. So we have a massive solar desalination process that's needed. Now, we've always had water for free in all of our lives. You just dig a hole in the ground and the water comes up. Well, that period of time is over. We're already on top of it. India is in the transition where there's a lot of places in India that no longer have water by digging a hole. Water came for free. Oil came for free. We'd dig up the oil and we'd burn it, creating the problem we have today. So these free economies where you can just get something out of the ground and use it and sell it for high prices, this is coming to a halt. So this cycle of the warming the water, okay, the massive desalinization is needed. How am I going to do that? Well, I'm going to use the sun to evaporate the ocean water, and then I'm going to condense the vapor by heating up the cold seawater. And I will explain this in much greater detail in a couple of minutes. So this cycle of heating the water to evaporating it and then cooling it using the cold seawater to bring the water vapor back to pure water is the essence of the idea. And when I brought this up and mentioned it to people who knew thermodynamics, they told me I was crazy, but fortunately I persevered. And it turns out I'm not crazy. It's true. It works. So the goal is to use the sun as the sole source of energy to heat the seawater, to create pure water from the water vapor. And then you'll end up with brine and pure water. So we need to know some numbers here. How do we do this? Well, here's the original idea. My brother is an architect, and when I told him this idea, he said, cool, and he made this drawing. About an hour later, he had the drawing finished. So I really like this drawing. So what this shows is you have the ocean over to the right, and there's a platform or a viaduct. There's pipes that bring the cold water, keeping it cold, so they're insulated pipes, up to a viaduct. This might be 100 yards away, and it might be 10 miles away, but there's a viaduct that carries the water, and the cross section of the viaduct looks like this. So there's channels where the water flows along in this direction towards what we're calling the freshwater lake. And the sun shines on this platform, and there's a glass film over the top or some kind of a plastic or visible, so the sun can get through. The important parts of the solar spectrum can get through this glass film, but the water vapor, which is heated to, it says here, 60 degrees centigrade, maybe it's 40, maybe it's 60, that's a number that needs to be determined. But the higher that temperature is, we don't want it to go to boiling, we just want it to be, like 60 degrees is like 120 degrees or something like that, Fahrenheit. So somewhere between 90 and 120 degrees Fahrenheit would be a good temperature, because once it gets to 90 degrees Fahrenheit or 40 degrees centigrade, the water vapor becomes a very significant portion of the liquid water. It's like 5% of the water vapor, the humidity, you can say. If it's 100% humid and it's 95 degrees out, you have 5% of the water as vapor, okay? And then you suck the vapor, that's not very clearly shown here. You suck the water through little teeny holes in these channels down below, and this down below is as cold as the water above. And so once the vapor gets into the underside of this platform, it's blown, it's very light because it's just water vapor. It's the density of air a little bit more, and it goes down here, and the cold water is at this end and the hot water is at this end. So when the water vapor meets the cold water down at the input end, it condenses, and this is the key to the whole thing. When it condenses, it heats the water above. So you have the water vapor down below and it's at 60 degrees, it goes on towards the cold water. It heats the cold water and at the same time condenses, giving us pure water. Now that seems to be, as best we can tell, an original idea. So the 60-degree vapor is condensed to 20 degrees or 15 degrees. You can't get it down to 15 if that's the temperature of the ocean. That doesn't work. That's against thermodynamics. You need to have some temperature difference, but 20 degrees would be good enough because there's an exponential relationship between the vapor pressure or the dew point of the water and the temperature. So you go from 5% down to 0.5% or less when you go between those. So I need to explain how this works, and I've got another video that I want to play for you, and then we're going to break to a Q&A so that you have an opportunity. So write down your questions. I'm going to play this next video right now.
Humanity faces an existential crisis like none it has ever faced before.
Is everything working? Can you hear it?
Can you turn up the volume a little bit on the video?
We heard it for a bit and then it stopped.
I stopped it. I don't think I want autoplay, right?
No.
The audio is up all the way. I don't know how the audio is getting to you. I'm going to start. We can play it again if you need to.
Climate change is not simply a matter of global warming. Severe weather, intense fires, and rising seas have huge impacts, aggravated by the demands of Earth's increasing population. Potable water and food are problems as serious as the implications of climate change.
I think I should start over again. It's only a 90-second video, and there was some distraction. So I'm going to just start it over again.
Our innovative approach to desalination uses thermodynamics to separate ocean water into potable water and salt. In Figure 2, we propose a synergistic single solution to the many. Humanity faces an existential crisis like none it has ever faced before. Climate change is not simply a matter of global warming. Severe weather, intense fires, and rising seas have huge impacts, aggravated by the demands of Earth's increasing population. Potable water and food are problems as serious as the implications of climate change. Our innovative approach to desalination uses thermodynamics to separate ocean water into potable water and salt. In Figure 2, we propose a synergistic single solution to the many problems facing humanity. With the sun as the sole source of thermal energy, we can heat the cold seawater to over 100 degrees Fahrenheit. Given this 1 square meter of solar input, 61 kilograms of water will be heated to well over 100 degrees Fahrenheit, raising the humidity to 5%, thus releasing 3 kilograms of pure water vapor. Scaling up, 1 square mile of the Sahara Desert is 2.6 million square meters, releasing 8 million liters or 8,000 tons of pure water each day. This amount of water can create thousands of huge lakes and arid deserts to grow plants. As these arid wastelands evolve into jungles, they will naturally remove the carbon dioxide from the air. Water and food will become a free resource.
The only exaggeration I'm aware of is become a free resource. That's not quite true, but it will become a resource that is within our grasp and will solve a lot of problems. So maybe it's not completely free, but by free, I meant it's free from the cost of the energy, which is really substantial. So at this point, I'd like to open it up for questions. Maybe Todd can read from the chat box, or we could have even live questions. It's up to Todd.
John, we did have one question from Judy, and she asked, what caused the CO2 buildup on Mars?
Well, what caused the CO2 buildup on Mars? My answer is that I don't think we know, because we can't go back a billion years. Maybe when we start exploring the surface, there's three rovers on Mars right now. This just happens to be an unusual time. So once the rovers can explore Mars, we can look for the water. We can try to figure out where the CO2 came from. But it's a pretty good bet that when the ocean was there, the CO2 was much, much lower. But we don't have any, I don't have any solid facts on that, but it certainly is an important question because we'd like to know what the history of Mars was. Mars is a very, very important thing to study because it is a prediction of our future.
Another question from Walter, asking, what do you do with the salt brine? Reintroducing the brine to the ocean would eventually raise the salinity. Many organisms can survive in a narrow salinity range.
Well, that's a very good question, and I've been asked that question so many times. The answer is in my talk, but in a word, to deal with it, there isn't that much salt. And we will not return it to the ocean. That would be pretty stupid because if you return the salt to the ocean, you'd put the carbon dioxide, the form of carbonates, back into the ocean. So that's the last thing in the world we want to do. Now, the other answer is kind of a side joke, which I'm not sure if it has any truth to it or not. One person said, oh, we'll take the salt and we'll mine the gold and we'll have gold coins pouring out from all of the salt. Well, I don't think there's that much gold in the ocean, but some people think there is. But the salt is actually worth something. And I will answer the question precisely in a few minutes.
Another question from Abrita. And could you explain once more the mechanics of how the water vapor cools down in the aqueduct system?
That is a very, very important question, which I am going to deal with in the next few slides, precisely deal with that.
Nathan asks, will this process help remove microplastics as well?
Well, that's an original question. In the first place, probably it will, but not enough to count, because you'd have to process the entire ocean, and the entire ocean would take a couple million years to process. It's so large. Here's an interesting number. The Lake Michigan, if you filled it at the rate that I'm talking about, it would take 100 million years to fill it. So it's a huge amount of water. And to create, and it's fresh water, of course. So to get rid of all of the microplastics, we would need to process at least half the ocean to get rid of half the microplastics. And I'm not sure that that's feasible. But you could certainly try to put a dent into it to reduce it. But I think we probably can find better ways than this process to do that. But I don't really have the right answer. I don't know.
Hillary asks, if you look at your own project as an investor, what do you see as the biggest impediments to this project? Political, technical, environmental, question mark.
Well, that question has been answered by some people recently, and there's a spread of opinions, but the major opinion that I believe in is that it's political. So the first is the science. So we have to prove the science so rigorously that nobody can question it. And we are doing that. And that will happen within the next few months, to certainly within a year. So we'll prove the science works. And then it's a question of, can you get investors to deal with this? And that's my last slide, is how do you encourage investors to come in? So I think there's, there was just an article in the Guardian about 3 billionaires who are dying to figure out how it's the best way to spend their money to solve this problem. And I wish I knew how to call up Bill Gates and talk to him, or Elon Musk, or these billionaires, because if we can prove this works, I think the funding will come forth. Was there another part to the question?
Just whether it was political, technical, or environmental. So it sounds like, I think you addressed those.
Yeah, I don't think there's any down downside environmental issues here. I think every single metric is improving the environment. And I had one person who strongly disagreed with that, but they said, what do you mean you're going to grow all jungles in the Sahara Desert? That's going to destroy the environment of the Sahara Desert, which I didn't have a friendly answer to that response. But I think all of the environmentals are on the plus side that I know of. And the technical is the science, and I think that's positive. So political is the biggest problem. If you've got people who don't believe in science, then they're not going to resonate to the scientific issue being valid, and then they'll come up with some crazy reason why. Crazy reason, that's my terminology. They'll come up with a reason why we shouldn't do this, because they don't believe in climate change. They don't believe it was man-made. I mean, who cares where it came from? I'm done with that question. I hope I answered it.
And then we have one more question and a comment. So do we have enough time for the fresh water to actually reforest the desert in time to avoid surpassing the threshold number of CO2 in the atmosphere? Is the time scale realistic?
I think it would take less than 100 years to convert. If we had the full system working, once it's working, if it's working, we can continue to build it. So we would slowly grow these jungles, as I'm calling them, these lakes, and populate the lakes with fish, and we need animals around to create, if we need food, so we'd grow plants. And I think that process would proceed on like 100-year time scale. And at some point, if we start taking enough carbon dioxide out, we'd slow the process of the carbonization. And at some point, we reverse it. I mean, right now, in the summertime, it's already going down. So if we can just, it's a very sharp tipping point. So my answer is, without further study, I think there's no problem. We just have to get to this. We can't wait a couple 100 years to implement something like this.
Then Alex, we had another one come in, asks, there was an ocean wind farm in the video. Did that serve a purpose in the process?
Yes, that's to pump the water out of the ocean so that we don't need more energy coming from thermonuclear or burning kerosene or something. So that it doesn't take that much energy to pump the water out of the ocean. You want deep water so it's cold. And when it goes pumped from deep up to the surface, it takes almost no energy because the water density doesn't change very much. But once it comes off the surface, then if water's pretty heavy and you got to pump it up as high as you want, and you'd like to have a gravity feed in this great big platform. So you might want to pump it up 100 or 200 feet, something like that. Think of this platform as being like a super highway. So I hope that answers that question.
And then lastly, Erhan, who's a fellow faculty member, had a comment about Mars. So he thinks, or he made the comment that it lost its magnetic field, and that because of that, losing its ocean could be linked to that process.
I think Erhan's probably right on. I'm not aware of that, but he knows more about it than I do.
So I think that was it.
John, I have a thought. Can I ask a quick question?
Sure.
Please.
Yeah. So thanks, John, for excellent questions, by the way, and that's great discussion. I just have one more question, which is, so it's really boiling down to creating freshwater lakes in places that have low vegetation and low and sparse amount of trees and plant growth, right? Is that the main point, John?
There are two large arid areas that need this kind of a treatment. One is, of course, the Sahara Desert, and you could convert the entire, I mean, it was a jungle millions of years ago, so we need to restore that. And the other is in Australia. And I read in the paper that if those two were forested, that would probably take care of the problem right there. So you need them. People talk about growing trees. This is very naive because you can't grow trees. You plant trees, they'll all die because they need water to grow. So you can't grow trees in the scale that you need unless you have fresh water. You can't put out the fires in California unless you have fresh water. You need to get the water out for lots of purposes. You got to grow plants. You need the water to put out the fires, to keep the soil moist so that the fires don't start in the first place. You need it to grow trees. So water is the cornerstone, the corner link to this whole process. Without water, we can't go anywhere.
So my question is related to that. Do we have back of the envelope calculations of how big a lake, a freshwater lake, do we need? Is it the size of Lake Michigan? Is it the size of a smaller lake? Because ultimately it seems like the cost of this project and the engineering of the project would come down to really getting the seawater all the way in the middle of this arid region, right?
I mean, if we ever get there, I plan to start in California, just north of San Francisco, maybe in the wine district. And we've identified there's a university and it's right next to the ocean, and and there's some desert there. We could just pump it out, and within 20 miles, we could take care of the whole thing and demonstrate that it works. So I don't think you're not talking one lake, you're talking thousands of lakes, which are small and relatively shallow, like 50 feet deep or something like that. So you need enough. By the way, the water will just sink through the sand and disappear. So you got to have enough clay underneath the bottom of the lake. And the clay comes from defecations from animals, or you have to put it there, or you put plastic down to keep the water from just going into the ground. So there's a lot of little details here, but I think I'm not aware of any that. One of the most difficult ones is you got this glass film over the top, and can't have a sandstorm. It covers up the thing. So, and that could be expensive as a double layered thermal pane with argon between the two sheets. So there's a lot of issues here that need to be dealt with, but they're all engineering issues as far as I know.
And you think none of them are showstoppers to the extent you've looked at them or you've thought about them?
I haven't found a showstopper, and when I find one, I'll talk more about that than anything. But everything I thought temporarily might be difficult, not a showstopper. And the showstopper is that the fundamental concept doesn't work, which I haven't really described yet. That for example, early on, we thought if you evaporate water, the salt might come up with it. It might still have some salt in it. Well, that's just not true, because the water vapor is just single molecules of water, and sodium chloride is much heavier than a water molecule. So that's not going to happen. So there are things like that. I think we've thought those through but that's why it's so important to have a working prototype so that there's no gotchas there that you didn't think about.
Very exciting. Thank you very much.
So I'll go on now. This is an important Q&A session, and it's surprising how similar this Q&A was to the one on Wednesday. There was a lot of similar questions there. So that means I'm either not doing a good job in answering the questions, or the Q&A is the best place to bring the questions up. Okay, so now I'm going to answer some of these details. So here's the makeup of seawater. And this works in our favor in a massively important way. No pun intended. So you have water, which is 96.5% of seawater is pure water, unadulterated water. And then there's 3.5%, which is composed of a whole bunch of different things, but most of it's salt. 55% chloride and 30% sodium makes up the sodium chloride. So it's less than 3.5%. So it's you can calculate what that is. And then the next most common element is sulfate. Sulfate, is that, I'm not sure that's an element. Is that a salt? I'm not sure. Sulfur is composed, sulfate, that's probably a salt. And then calcium, and then potassium, and then all sorts of other stuff, presumably also including gold. This is a very, very important thing, because when we start removing the salt water, or the water from the salt water, how much of it can we take out before we get into trouble? So CO2 is only 0.04% compared with, that's the 400 parts per million. If you calculate 400 parts per million, if you put that in terms of percentages, only 0.04%. And yet, with that tiny amount, oh, I'm sorry, I'm thinking of the salt. I'm talking about the CO2. I'm not reading my own slides. So the carbon dioxide is only, some of what I said is true, is only 0.04%. That's the 400 parts per million of the carbon dioxide. The sodium chloride is more like, 3%. Okay, next thing, and this carbon dioxide that is absorbed in the ocean is the source of the dropped pH, or the increased acidity. And that causes the destruction of the coral reefs, which I'm sure we're all very aware of. And the life in the ocean is largely built around these coral reefs, at least some of it is. Probably not large sea mammals, but there are plenty of other life that's critical to the ocean. So another point is, when you evaporate seawater, it leaves the salt behind, concentrating the salt in the seawater, and the water vapor is hot water. It's in vapor form, which is just molecules of water. Now, the water can be used to grow plants, which will then consume the CO2. So this should not be forgotten. One of the main, we need water for a lot of things. To wash our hands, to get rid of COVID-19, we need water to drink. We need water for survival, to grow plants. But the reason why we're generating it in this, we may need to get a drink of water. We need to grow plants. You cannot grow plants in seawater. Excuse me.
John, can I stop you there for a second and just ask a related question that came in? Are you aware of anyone working with genetic manipulation to allow trees to propagate with salt water?
Yeah. Good luck is what I say. I may need to go get a glass of water. I don't think, there are some plants that grow in seawater, so it's not impossible, but we need water anyway. So if you get plants to grow in seawater, that helps. I'm open to anything that works. So if you can make plants that grow in seawater, you still need pure water. And they'll probably grow better in pure water than they will in salt water. Okay, massive desalinization. How does it work? Well, right now we got about 420 parts per million, and that tips the energy balance, as you have seen. And I'm saying we can use direct sunlight to heat, and then evaporate the cold 15-degree seawater. But how? Okay, so here's the scenario. We put the seawater in this platform exposed to the sun, and it heats the seawater up to, let's say, 100 degrees Fahrenheit, or 20 degrees, 30 degrees, 40 degrees. 40 degrees is 100 degrees centigrade approximately. Our body temperature is 37 degrees centigrade and 98.6 Fahrenheit. Okay, water vapor is pure, has no salt in it whatsoever. The water vapor is then cooled using the cold 15-degree seawater. So once we get the 40 to 60 degree water vapor, then we propagate it. And remember, it's very light, so it doesn't take very much energy to push that. It's basically air with the 5% water vapor in there. We pipe it underneath the aquifer. We had this platform. So it goes underneath this aquifer or viaduct. And there it's exposed to the same temperatures as the water above, and then you push the air down so that it sees the cold water, meets with the cold water. And when the vapor hits the cold water through a heat exchange, which is very simple, it cools the water vapor, and once it gets down to 20 degrees, you basically have almost 100% of the water vapor back in the form of pure water. But the really cool thing is that when you cool the water vapor, it has a huge amount of latent heat energy in it. When you cool it with the cold water, you heat the water. So now the cold water is being heated by the sun, and it's also being heated by the condensation of the water vapor. And this is a big deal. This is what makes it work. It increases the yield. And if you had the walls completely insulated and you're not losing any heat through the walls, which just is styrofoam packing, you basically can get this thing to 100%. Now, I don't think we're going to get it to 100%, and I'm not trying to, but if we got it to 95% or even 90%, that would be good enough. So here's the basic equation. You start with seawater, 1 kilogram, and you heat it with the sun, and that produces water vapor. Well, how much water vapor can you get? Well, you can get 93% water vapor. Where does that number come from? Well, that's when the H2O is twice the amount of salt. So you have 1/3 part salt and 2 parts water vapor. I mean, pure water. This is the brine. And this, you have to stop at this point, because when you evaporate more water out of the brine, the salt starts to precipitate. Now, that's a number that's told to me, that it's like 30%. So, and once it precipitates, it's going to gum up the works. And you've gotten 93% of the water. I mean, don't be a hog. I mean, this is a pretty good yield. You're taking 1 kilogram and 93% of it's turned into pure water, and you have this brine. You pour the brine out on the ground, and you let the sun go at it a little bit more, and pretty soon you just have the salt. You shovel up the salt, and you go and sell it. And it's not very much. It's just grams. So the seawater gives pure water, which gives brine, and 100% solar powered. There's no inefficiency, such as solar panels, which you may or may not know that solar panels have a maximum efficiency today of 23%, which means 77% or 4/5 of the energy is lost. This is a huge hit on solar panels. Solar panels are not the solution to the future, in my opinion. I'm not saying they shouldn't be used, but it's our best bet today, but they're pretty inefficient. And to make them more efficient is very, very expensive, and you're not going to get much more out of it. I don't think. That's my understanding. And people in my department know a lot more about this than I do, and I've asked them. So that's the answer I got. There's no power-hungry reverse osmosis. Reverse osmosis is one of the main methods used to desalinate water today. It's heavily power-hungry, and they have to process the membranes to get clogged up with the salt. It's a big mess. It's not, anybody who knows about RO will tell you it's not the ideal solution. They'd love to find ways of improving it. So this method I'm proposing, my position is that it's ultra green. I'll take a quick question, 1 or 2, but not more, because I got to keep going here.
No more questions at this point.
The main question is, how much of the heat of vaporization from the condensed vapor can be recovered? So how do you do that? How do you get so you've taken the water, you've heated it to 40 to 60 degrees. You've got this very hot water vapor, pure, and it's got a huge amount of energy in it. It took a lot of energy, however much energy it took, to get it from 20 degrees to 60 degrees. That was a lot of energy, because it's a kilowatt per square meter, and you've got, a couple hundred square meters or more. You got a square mile. And so there's a huge amount of energy, and that energy is sitting there in that water vapor, and you can't just, push it out the door. The first thing, you have to condense it. So where are you going to get the coldness to condense it? Well, you've got cold water coming in, 20 degree, 15 degree seawater. So you've got to get that water vapor in contact through a heat exchanger and use it to cool the water vapor. And in the process, you're going to be transferring all that thermal energy to the cold seawater. Therefore, you're heating it. So you're getting all the heat back. It basically comes up with the integral of all of the thermal energy you put in from the sun is being used to process the cold water coming in. So it's a super, super big hit. By that, I mean, that's why you can approach efficiencies of up to 95% and possibly even more. So thus less sunlight is needed to reach the critical temperature, T max, because you're not only heating it from the sun, but you're heating it from the previous sunlight, which is in the water vapor, the energy there, and you're using that to condense the water vapor and thereby also heat the cold water some more. So this results in, I don't have a hard number here, but I'm saying it's going to be the only heat lost is the heat loss due to heat radiated off the sides or off the glass. I mean, you got the water vapor temporarily underneath the glass, and above the water, you got to suck it down. You don't want the heat to be lost through the glass. And I think you need a thermal pane or some kind of a decent thing. That's one of the critical things that you got to really look at carefully. Concept: flow the water vapor underneath the inlet for the seawater, exposing it to the inlet seawater, cooling the vapor, further heating the seawater. So that's the whole concept. If you followed what I just said on this slide, you got it. Who will pay for it? This is my last slide. Well, the billionaires who made all their money on the railroads, that was circa 1870 and beyond, that's when they put the railroad across the United States. They made all their money on the railroads. This is billions and billions of dollars because there was a need for inexpensive transportation, and the railroads turned out to be the answer. And how were they driven? Steam engines. They'd boil water and they'd use the steam to run the engine. Nobody really understood the technology, but they knew it worked. Today, we have another huge need. We need cheap, clean water. And that was easy. We just pump it out of the ground. I live on top of the Muhammad Aquifer. I don't need any cheap, clean water. I got free water. Well, that period of time is coming to an end. The water industry today and the transportation industry of 1870 have a great deal in common. So in other words, if you want to become a billionaire, get into this business. There's a huge opportunity here. Clean water is equivalent to megabucks. Whose opinion is that? It's my opinion. A business model needs to be thought out, and that's the end of my talk. And I'm open again for questions, comments, or just plain good old thoughts. Is anybody there?
Yes, we are. I'm just monitoring the chat to see if any other questions come in.
So John, can you build some prototype? I mean, how big of a prototype do you need for the principles to be demonstrated?
Excellent question, and I have an answer. So last semester, ME 470, which is a mechanical engineering senior design project, they tried to make one, and they did make something, but it had a lot of little minor flaws, like it leaked salt water into the fresh water. And there's a lot of problems. Let's not talk about what they are. So this semester, we're doing it all over again. We have 4 new students who are working on this as we speak. I hope they're at this talk, but can't guarantee it. But we had a meeting yesterday about what kind of progress they make. So to answer your question is 1 square meter of evaporation chamber and 1 square meter or less of condensation chamber, and make it modular with little pipes, tubes going between the two. So that's the mistake we made last semester was we tried to make the whole thing in one great big thing. You couldn't pick it up. 10 people couldn't pick it up. It weighed, 1,000 pounds. It didn't weigh 1,000 pounds, but it weighed hundreds of pounds, and it couldn't be moved because it would fall apart. Now we're making a modular system, and we have a pump, an air pump that blows the water, and we have a valve that controls how fast the air flows and how fast the water flows. And we have a cooler to provide cold salt water. And so a small table will carry the prototype. And then I have more to this answer, but I'll stop because I think I've answered your question, Bruce.
Okay, the answer is 2 meters squared.
Yeah.
More questions coming up in the chat. Todd, do you want to take them?
Yeah, let me see here. So Gareth says, I didn't quite understand how the water vapor is transferred below the salt water and how they are kept separated. Could you explain this a bit more?
Yeah. So I don't know how to get back to that. So the water channel, there was the video that showed that, and I'm not sure where it went. So in this video, there's a very brief sign right here.
61 kilograms of water will be heated to.
You see those little holes right there? So the water vapor comes off, and this is the glass. The sun is coming down here, and there's a slight vacuum which sucks the water vapor down below. And this is showing the water vapor going down below. And this is an aluminum. This is made of aluminum, or a good conductor. So the hot water is in contact with this aluminum sheet. And so when the water vapor goes down below, it meets the 40 or whatever the temperature of the water is. And then you suck it down to the other end and it gets colder as it gets towards the colder water. This is, by the way, a chart showing the percent of water vapor that you have as a function of temperature. So that's my answer to the question. It's actually, there might be other ways of doing it, but that's at least one way.
And then Alex asks, wouldn't having a glass pane above the condenser trap heat, which would impede the condensation of water?
No, because the light goes in and the heat is blocked from going out because it's a thermal pane. And I'm having trouble getting rid of that side panel. So you have a glass pane. It's a thermal insulator, but the sunlight goes through it because it's glass. And the sunlight doesn't have, sunlight, you don't feel the heat until it hits something and then heats it up. This last summer, I sat down in my car and the sun had been shining on there. It was like 100 degrees out, and it was up near Chicago. And I had shorts on, and I almost burned my leg from the heat that was heating up my my seat of my car. And inside the car was hot, and the windows were all closed, and sun was coming through gangbusters. And that's an American expression. I hope I answered the question.
It's basically a greenhouse effect, right? It's a greenhouse under that glass.
But the formal definition of greenhouse is a little bit different, but it's like a greenhouse. But yeah, greenhouse, the light comes through, heats up inside the greenhouse, and humidity gets high inside the greenhouse. That's exactly right. You can trap the heat inside the greenhouse, which is what a greenhouse is for. The term greenhouse effect is a little bit different, but it's a related concept.
Abrita asks, the condensation is happening in a chamber under the channels carrying the liquid seawater?
Condensation is in this lower channel down here. So you have water here. It's being heated. The water vapor comes up. It's 5% by mass, at 40 degrees, and it's higher even more. As you can read that off this chart, it's 5% at 100 degrees Fahrenheit. And then it's sucked down. So we have a slight negative vacuum, very small vacuum. So the water vapor comes down. You'd like the water vapor to be close to 100% in this region. So what you're sucking down is mostly water vapor. So then once it gets down below here, it continues to be sucked towards the cold end. And as it moves towards the cold end, the temperature is dropping as it goes towards the cold end, and therefore the amount of water vapor is dropping. And by the time you get to 20 degrees, it's all been converted back to water. But as it cools, it gets its cold from the underside of the panel, which is at the same temperature as the local water. And so that energy that causes the condensation goes into heating the water above.
I think there was one question earlier from Karen, and the question was, what kind of team have you put together? Any grant funding? Question mark.
I have my brother, the architect. I have the team of several other professors in mechanical engineering. I've collected a large cadre of professors who are interested and express verbal commitment, but nobody's put any money into anything. I think then we have to proceed in steps. So the first step is to demonstrate it so categorically with a prototype that nobody's going to question whether it works. I've had very high-level professors in the university, I won't say names, who told me it couldn't possibly work. And I believe there's a reason I don't want to say their names is because I believe they're wrong. So I've had a lot of people laugh at me, but at this point they're not laughing anymore. I can't even remember what the question was. Oh, do I have any support? I have support. In the most important support I have is the mechanical engineering department, and Professor Quinn Brewster has a great deal of enthusiasm for this and is working hard with the team of 4 mechanical engineers on almost a daily basis, and I'm participating in that as well. And that is our really hardworking, actively at work team of 4 undergraduates, competent undergraduates working on this thing, with Professor Quinn being their advisor, and I'm called a sponsor of this project, which means I'm supposed to pay money, which last semester I actually did pay some money. So it's minimal, but it's enough to prove that it works. And I think we will.
Question from Mark. What does 97% efficiency mean compared to quote unquote latent heat of solution or some such?
First, 97%. I'm not sure. 97% was a number that I had. 97% of water, seawater is composed of 97 approximately percent of pure water, and it's actually 3.5% salt. That's the only place where 97 appears. So I'm not sure which number there was, but I have this number 95%. This number is a guesstimate from me. I'm saying if you really could run this reversal process, how do you recover the latent heat? All the energy's in the latent heat of the water vapor, and you got to get that out and use it to heat the cold water coming in and recover all of that latent heat. If you don't recover the latent heat, the whole thing doesn't work. I don't know if I answered the question because I wasn't clear exactly what the question was. Maybe.
We can ask Mark, and Mark, if you want to put in the chat if that answers your question. Hillary asks, what's powering the vacuum that pulls the water down? Is electricity needed that would be powered by the windmills?
Good question. The first place is, if you want to pump water around, it's very heavy and it takes a fair amount of energy, a fair amount of electricity, and that's what the We have some electricity at the far end, and that could be used to power a blower. But when you have water vapor in air, the density is a little bit heavier than air. You could take it to be the same density as air. It's not density of air, it's heavier, but not very much. So you can suck, you put your mouth on this thing and suck, and that's enough vacuum. It doesn't take very much. 1/10 of an atmosphere, or even less, 1/100th of an atmosphere is probably going to be enough to suck the water vapor back towards the cold end. But the reason why you can't just do it that way is because there's going to be leaks all over the place. And you have to keep the water vapor so that it doesn't leak into the atmosphere. It doesn't leak into back upstream up into where the water vapor is coming from. So you're going to have to isolate the water vapor as it comes down and have lots and lots of compartments with the water vapor. You'll be pumping it around. It's like your air duct in your furnace, okay? One little fan down in your furnace can blow a lot of hot air up into your house. It doesn't take as much electricity, for example, if you have a boiler that's heating water and putting steam in. Well, even steam is light, but pumping hot water around is energy consuming, but pumping hot water or steam or air around doesn't take that much energy. So even if you had to have, some source of energy, you could run the wires from the generators that are in the ocean. You could get more than enough energy for free that way. So you want electricity, you have light bulbs, you want light bulbs, and you're going to have some other electricity. I'd say the light bulbs are going to consume more energy than the fan that is required to suck the water vapor down. But this is a number, it's easily determined because we understand the physics behind that pretty well.
So Mark, who had the question about efficiency, 97% efficiency, said he meant energy efficiency. And is there some theoretical minimum amount of energy to remove the salt?
Well, we have a lot of energy to remove the salt. It comes from the sun. It's one kilowatt per square meter for 5 hours a day. So you have to decide, how do you want to calculate the efficiency? If you include the solar input, it's not very efficient at all. Or you could say that energy is free, the solar input's free, so it's 100% efficiency. What determines the so-called efficiency? It's the heat that is lost. You have 40 to 60 degree water vapor and water, and that could be thermally, you got a hot surface, and then the outside is at room temperature, or it might be at the temperature of the Sahara Desert, or it might be the temperature of the Southern California coast. So there's an outside temperature and an inside temperature, and any heat that transmits through the walls of the container is heat that's lost, and that determines your efficiency. So styrofoam has a very, very large insulating factor, and it's pretty cheap. So you could use, we're going to need a lot of styrofoam. Invest in styrofoam if this thing ever gets going, because that's going to be a good company. It's probably DuPont. So we need a lot of styrofoam. 3 inches of styrofoam will keep the heat from getting out altogether. You also build thermopanes, but they're very, very expensive. So by comparison to styrofoam, you have 2 pieces of glass, and then they put a vacuum between them and fill it with argon. So it's not a vacuum anymore. And that's an extremely good insulator. That's the Anderson thermopane. So we're not going to go buy Anderson thermopanes because it's too expensive, but we do need to find a solution to that. If anything is the most difficult problem to solve, it's that. What are we going to use to cover the top of this to keep the heat in, but allow the sunlight through? That is a problem that needs some work. I hope I answered the problem about efficiency. I think I did.
And Mark is unmuted. So Mark, if you want to chime in, you're free to.
Okay, sorry about that. I had Bluetooth problems with my computer, so I was listening on my phone on YouTube, and there was a time lag and all that. So sorry about that. Anyway,
Is this Mark Cars?
Excuse me?
Is that Mark Cars? Are you Mark?
No,
Cars? Okay.
Mark Spiegelin.
Okay.
I'm not sure what my phone ID looks like. Oh, wait, I'm not on Zoom on my phone. Anyway, all that aside, I assume I only vaguely remember my chemistry. There's some, when you dissolve a salt in pure water, there is presumably, I'm guessing, some heat released, and we have to pay that back to get the fresh water out. And so your main trick, it seems to me, apart from insulation and all the other details, is basically recovering all the latent heat you put into the water to heat the initial water. So you get a greater amount of fresh water out of a given amount of solar flux. So a smaller installation will produce the same amount of water. If you just did it, stupid by evaporating the water and condensing it and not recovering any of the heat, that would be part of the efficiency factor. So
you'd lose all, you'd have
you
horrible.
mostly answered my question, let's put it that way. But that was the intent of the question.
Well, let me have a quick response here. I don't think it's true that if you take water and measure its temperature and then throw in 3.5% by mass of salt, I don't think the temperature is going to go up.
Yeah, well, enthalpy, entropy, whatever. The basic principle of physics is you don't get something for nothing. So there is no even theoretical way, I assume, of desalinating water somehow for free, energetically speaking. And if that's true, that energy must go in at some point.
That is
I'll do some research. You don't have to address it further.
No, what you're saying is very, very true. If you just take salt water, the salt goes in and becomes ions of chloride and sodium. And if you try using electrolysis to remove it, it's going to take a lot of energy to split. You can't split the salt. I mean, it's already split as ions, but if you try to do it, you can do that. If you'll get a buildup of potassium on one electrode and chlorine on another, and now you got live chlorine to deal with, which is a deadly gas. I looked at it, and it's not a very good idea, and it's not energy efficient. It takes a lot of energy to do it.
Yeah, yeah. Okay, well, I don't want to take up more time with this issue. I'll go do some reading. Thank you for taking my question.
John, we did have one other question. Do you have to carefully control the inflow rate of seawater so there is enough cold water to condense the water vapor, but not too much to inhibit the evaporation from happening in the first place?
This is a very, very interesting question that we're dealing with, but the simplistic answer, the best one I can come up with, is the area of the cold seawater coming in could be 10 miles wide, and the area or the width of the channel of the brine coming out could be 100 feet. So you could have a lot of cold water coming in. You're evaporating the water by heating it. And so the volume of the water is going down to, 7% from 100%. And the saline is staying in there. So it's very easy to collect more cold water. And then how fast you evaporate it determines how much you have left after you started to evaporate it. So you have large amounts of cold water coming in, and as it evaporates, it's going to dissipate and disappear. And it's disappearing. Where is it disappearing to? It's disappearing into water vapor, and then you're putting it back into the cold water. So people were very concerned about this problem, and they said, you're never going to have enough cold water to make it work. And I just don't agree, but that's part of demonstrating that we can make it work. It's a good question.
Okay, I think that's, we don't have any further questions. Uh, Perhaps this is the time to wrap up. Uh, Thank you, Professor Allen, for this very exciting talk and giving us so much to think about and to read up. Um, Also, thank you everyone for attending this talk. We will send out further announcements for the upcoming talks, so please stay tuned. The next talk is about COVID-19 and what we did in the UIUC campus. And please tell your friends and family and other people to join in. And with that, we bring this seminar to a close. Thank you for everyone for joining in, and stay tuned for the next one. Bye-bye. Have a good weekend.
Bye. Thank you, John.
Thanks, John.
Thank you, Romit.
Thanks.
Thank you, everybody.